Welcome to the second lesson in which we will learn about the main types of radioactive decay. In the last lesson, we discussed that radioactive atoms decay. Radionuclides can undergo different modes of decay, which are classified by the type of particles emitted during the process. What type of a radioactive decay will occur can be found in different databases, but also in nuclide charts. Let's now discuss the different decay types, starting with beta-minus decay. Beta-minus decay occurs when a nuclide has too many neutrons in relation to protons, which makes it unstable. To get to a more stable state, a neutron should be converted to a proton. In this conversion, a beta-minus particle and an antineutrino will be emitted. The general equation here shows that in the beta-minus decay, a nuclide, let's call it X, decays to another nuclide Y. Y will be another element, since in beta-minus decay a proton will be added to the newly formed nuclide. Therefore, the atomic number Z on the bottom left will be increased by 1. The mass number A doesn't change, since we now have one less neutron but also one more proton. So the total number of protons and neutrons is conserved. The beta-minus particle is actually an electron, but it is called a beta-minus particle to distinguish it from the electrons orbiting in the electron shells. The beta-minus particles originate from the nucleus and not from the electron shells of the atom. Note that beta-minus decay also results in release of energy, shown here in the equation. This energy will be divided between the beta-minus particle and the antineutrino. Here you can see an example of the decay of carbon-14, which decays to nitrogen-14 by the emission of beta-minus particle. The total energy released by this decay is 0.156 MeV. On this slide you can see how we can use the nuclide chart. Since in beta-minus decay a proton is gained and a neutron is lost, the newly formed nuclide can be found up to the left from the original nuclide. Note that across this diagonal the mass number of all nuclides are the same. Since the energy emitted in beta-minus decay will be divided between the beta-minus particles and the antineutrinos, the beta-minus particles will have an energy spectrum rather than a single energy. The beta-minus particle has maximum energy when the antineutrino particles do not receive any energy. Now, what happens if a nuclide has too many protons? In this case, a proton needs to be converted to a neutron. Here you can see the balanced equation for beta plus decay. This decay produces a new element with one fewer proton, so the atomic number Z decreases by 1 for the newly formed nuclide Y. The mass number A remains the same as a neutron is formed in the process. The beta plus particle that is emitted is called a positron and is actually a positively charged electron. Energy is again released in this decay. In fact, all decays are associated with the release of energy. This energy will be divided between the beta plus particles and the neutrino. On this slide, an example of beta plus decay is shown for carbon-11. Carbon-11 decays to boron-11. Boron has 5 protons, one less than carbon-11, but the mass number for both is still 11. In this figure, you can see that this nuclide does not decay 100% by the emission of a beta plus particle, but also by another process abbreviated here with EC, which stands for electron capture. Electron capture decay process will be discussed next. On this slide, you see how we can use the nuclide chart to determine which nuclide will be formed after beta plus decay. Since one proton will be lost, we move down to the right. The mass number remains unchanged as neutron is also formed in the process. Similar to beta-minus particles, beta-plus particles also have an energy spectrum with a maximum energy, which will be obtained when the neutrino does not receive any energy. Beta-plus particle emission will always be accompanied by the emission of 2 gamma rays, photons, of 511 keV emitted in opposite direction. This happens because beta plus particles are a form of antimatter. When they encounter electrons, they are instantly annihilated, releasing energy in the form of 2 gamma photons. This means that beta plus decay should provide at least 1022 keV in order to occur, which is equal to the energy of the 2 emitted photons. So what happens if a proton-rich nuclide cannot provide this energy but still has too many protons? In such cases, the nucleus will capture an electron from the nearest electron shell and will convert a proton to a neutron. We call this type of decay electron capture. Electron capture also results in the emission of a neutrino and the release of energy. In this case, all the energy will be given to the neutrino. Identical to beta plus decay, the newly formed nuclide Y has one proton less but the same mass number 6. Beta plus decay and electron capture are competing processes, which is why you often see that a nuclide that decays by beta plus decay will also partially decay by electron capture. Here you can see an example of a nuclide that decays primarily by electron capture. Since one proton is removed from iron 55 to be converted to a neutron, Z is reduced by 1, while the mass number remains the same. This corresponds to a step down to the right on the nuclide chart. Another type of decay is alpha decay. It usually occurs in nuclides with many protons and neutrons, making it characteristic of heavy radionuclides. In such cases, the radionuclide will expel 2 protons and 2 neutrons in the form of a helium nucleus, as shown in the general equation. You can see here that the mass number of the newly formed nuclide Y will be reduced by 4 and the atomic number by 2. We call such an expelled helium nucleus an alpha particle, and this is why we refer to this decay type as alpha decay. An example of alpha decay is polonium-210, which decays for 100% by the emission of an alpha particle. This decay route of polonium-210 is shown in the nuclide chart here. Since the nuclide loses 2 protons and 2 neutrons, the mass number will be reduced to 206 and the atomic number will decrease from 84 to 82, resulting in lead-206. This corresponds to 2 steps down to the left in the nuclide chart. After alpha, beta minus or beta plus decay, the nucleus will remain in an energetically excited state. To get rid of its excess energy, it will emit gamma rays. In the general equation on the slide, the excited state is denoted with a star symbol. Thank you for watching this video. In the next lesson, we will talk about what happens with radiation once it is emitted.